I opened the code we worked on last time, and this time, when we control the PWM, we have the blue LED on our module, right? We will control the blue LED to gradually brighten and dim using PWM, which stands for pulse width modulation, a technique used to encode a message into a pulsing signal. First, we will clear the code, ensuring that all previous configurations and settings are reset to their default states. The red board has PWM I/O, which includes pins for out, down, up, high, down, and sleep, providing a versatile range of input and output options for various applications. We will set the mode, flow, LED, and frequency to a fixed value of 5000 for now, which is a standard setting for many LED control applications. Initially, the duty cycle will be set to 0, which can be configured in 16 bits, allowing for precise control over the LED's brightness levels. Since it is 16 bits, we can set it based on 2 to the power of 16, which is 65,536, providing a wide range of possible values for fine-tuning the LED's behavior. I will explain this further later, providing more detailed insights into how PWM works and its applications in LED control. In the while-true loop, the variable I will change from 0 to 99, incrementing gradually to create a smooth transition in brightness. So, the process begins with the value increasing in brightness until it reaches the number 49. At this point, the brightness is at its peak. Following this, the value will start to dim, beginning from 50 and continuing up to 99. This cycle of alternating between bright and dim states is continuous and repetitive. If the value is less than 50, it becomes necessary to truncate the decimal for the display purposes. This means that the value will be shown as whole numbers such as 65, 35, and 36. However, in practical terms, 35 is the final value in this sequence. This final value, 35, will be represented as a percentage, which is crucial for understanding the output. The percentage representation is significant because it results in a value known as IE, which is an important metric in this context. For example, if it's almost 50, it would become 100. Since it's 100 out of 100, it will become 1. Then, it will be 6, 5, 3, and 5. So as this percentage approaches, the value of I getting closer to 49 means that the brightness is getting closer to almost 100%. Then, in the else case, since it is getting darker here, it is about reducing the brightness. This means that we need to focus on gradually and carefully adjusting the settings to ensure optimal visibility and comfort. In this way, so from here, it goes from 50 to 99, right? For example, if it's 50 here, then it would be 0. In terms of percentage, that's 0%. If you multiply by 6535, it will obviously be 0, and I will go from 6535 to 0%. Since it drops almost from 100% to 0% when it is at 100%. And as it gets closer to 99, this part will eventually become almost 100%, right? So if you subtract 100% from 100%, it practically brings the result close to 0. So here, to put it simply, it eventually becomes almost 6, 5, or 3. Here, it actually goes from 6535 to gradually reach 0. This is the kind of code we have. So, since this, one method runs every 0.02 seconds, which is about 20 millisecond. If you multiply 100 by 20, it will be almost 2 seconds. Now let's run it once. As you can see, the blue LED is brightening and dimming at about 2-second intervals. In this session, we worked on controlling PWM with CircuitPython. Although the frequency is fixed at 5000 for PWM control, if I want to change the frequency, each time when controlling the piezo speaker buzzer later, I can change the frequency during operation. Even if it is fixed at exactly 5000, you can change the frequency while operating to alter the sound. I will explain that again when I have the opportunity later. Then, I will see you next time with another topic.